This video will talk about how to calculate boiling point elevation, the change in boiling point, and figure out the new boiling point, and the change in freezing point, and figuring out the new freezing point of a solvent. First thing we need to know is the equation that we'll use, and it's delta T is equal to KMI. Now, giving you each of the terms and the units that you should put them in. So delta T is the change in temperature, and that's going to be recorded in degrees Celsius. K is the mole freezing point or boiling point constant, and that's something that you would base on the solvent and you would look for in a table. Now, its units can come in two ways. It can come in terms of degrees Celsius times kilogram over mole. And all this is right here is 1 over the molality, because molality is moles per kilogram. Or it can come in degrees Celsius per mole. So the molality would be on the bottom. Same thing, just a different way of expressing that unit. M for molality, or moles of solute per kilogram of solvent. And then I is the number of particles, which we call the Van 't Hoff factor. So we learned about the Van 't Hoff factor in the last video on coligative properties. Now, what this calculation is going to allow you to do is figure out how much the freezing point changes or the boiling point changes. And what you're going to have to do with that information is adjust the actual or the normal boiling point or freezing point of the solvent. So to find the new boiling point, we would take the normal boiling point of the solvent and we would add how much it changes by. Since this is boiling point elevation, we're adding the change in temperature. The freezing point, a little bit different. The new freezing point is going to equal what the normal freezing point is minus the change in temperature, because freezing point is depressed when you add a solute. And you can find a table in your textbook. This is another version where you can find a bunch of solvents, their normal boiling points, their normal freezing points, and their constants. Okay, how much they change by per molality. Okay, so here's our first example. It says, at what temperature will a solution that is composed of 0.73 moles of glucose in a 0.225 kilograms of phenol boil? And it gives you the normal boiling point of the solvent, that's phenol. So if I was looking at a table to figure out, okay, which one of these am I going to use to find the KB, I would not look at the solute. I would not look at the glucose, even though glucose is probably not going to be on there. I would look for phenol. Okay. So the normal boiling point of phenol is 181.8. And its mole boiling point constant is 3.60 degrees Celsius per molality, per mole. So really what it's saying is that for every kilogram of this solvent, if I have a mole of the solute, it'll change by 3.60 degrees. Okay, so I'm going to split this up into given and work. So on the left side, I'll list my givens. So I know that I have to figure out the new boiling point. It says, at what temperature will the solution boil? So we want the new boiling point. I know the normal boiling point, either from a table or listed in the problem, is 181.8. In order to figure out the new boiling point, I'm going to have to figure out how much the temperature has changed by. And also in the table is the mole boiling point constant. I do not have the molality, but I do have some information that will allow me to calculate molality. Since molality is moles of solute per kilogram of solvent, I'm just going to take the moles of glucose and divide by the kilograms of the solvent phenol. So that's 0.73 moles divided by 0.225 kilograms. Now, if these were in grams, you'd have to convert it into kilograms for the solvent. For the solute, if it were in grams, you'd have to convert it into moles. So that works out to be 3.2 with two significant figures. The Van't Hoff factor. Now, the Van't Hoff factor, I, is the number of particles this is going to break down into. Now, I've already told you it's 1, but the reason it's 1 is because this is glucose. Glucose is not an electrolyte. It contains carbon, hydrogen, and oxygen, which are all nonmetals. So it's going to stay intact and just be 1 particle. Start plugging that into the equation. The change in the temperature of the boiling point. Notice it has a subscript B now. That's because we're changing the boiling point. Is equal to the equal to the mole boiling point constant times the molality times the Van't Hoff factor. Plug everything in. And cancel out units that will cancel. So the molality cancels. And I get 12 degrees. Now, this is only one part of the answer that I need. So it's saying that it's going to change by 12 degrees Celsius. We want to know, what is that new boiling point? So I've got this part, just got to figure out the new boiling point. And so remember that to figure out the new boiling point, you're going to take the original boiling point of the solvent, the 181.8, and we're going to add that 12 degrees Celsius. And that works out to be 194 degrees Celsius. I've rounded this to the ones place because this measurement is rounded in the ones place, and when you're adding, it's to places. Okay, example 2. Find the freezing point of a saturated solution of sodium chloride containing 28 grams of sodium chloride in 100 milliliters of water. And we have the values. So we could look at a table, and if we were looking at a table, where would we look for? We would look for not the solute, sodium chloride, we look for the solvent, water. So again, I'm going to break this down into the givens and the work. The givens are going to take more work this time since I don't have everything in the units that I need. So let's see what I need. I need to figure out the new freezing point. I know that the normal freezing point of water is 0. I need to figure out the change in the freezing point. So the subscript is F this time because it's freezing point that's changing. I can look in a table to figure out the mole freezing point constant for water, the solvent. And this time you notice I have that in degrees Celsius times kilograms per mole, or per mole, excuse me. Then we've got to figure out, kind of got ahead of myself. We need to figure out the molality of this solution. Now we have the grams of solute. We need the molality. So we'll take the grams and turn it into moles and put them over the kilograms of solvent, which is water, which is also in a unit that I'm going to have to adjust. So 28 grams of sodium chloride times 1 mole over 58.4 grams to change grams into moles. And I get 0.48 grams or 0.48 moles of sodium chloride, the solute. To change the milliliters of water, the solvent, into kilograms, I have to use the density of water. And I know that water, for every 1 gram of water, I have 1 milliliter. So I'm using that density to do that, which really just means I have 100 grams of water. Okay, then I'm going to change that into kilograms. I know that 1 kilogram is 1,000 grams. And so that works out to be 0.100 kilograms of the solvent, water. So take that information, figure out the molality. So that's going to be 0.48 moles over 0.10 kilograms, giving me a 4.8 in terms of molality. Okay, and we need the Van't Hoff factor, I. Now this time we have a metal plus a non-metal. Sodium's a metal. And so I'm going to draw a line here. That's sodium and chlorine. That's 2 ions. So that breaks down into 2. There's all of our information condensed. Let's plug it in. So we want to find the change in temperature for the freezing point. That's going to be equal to the constant times the molality times I. Okay, and so here I've gotten my freezing point depression constant, and it looks like I changed it into this, into degrees Celsius per mole, just so I can work with the molality unit. Remember, they're the same thing. So if you ever see one that was in that other way in terms of degrees Celsius times kilogram over mole, just change it to look like this. So times the molality times 2, molality cancels, and you get 18 degrees Celsius. Okay, that's how much the freezing point has changed by. Now we need to figure out the new freezing point, and since freezing point is lowering, it's a depression, we're going to take the original freezing point, 0 degrees Celsius, and we're going to subtract 18 degrees. And so that works out to be negative 18 degrees Celsius. Okay, hope that was helpful. Bring any questions to class.